Okay, tree diagrams. It comes up in maths quite a lot and comes up in statistics. We're going to be talking about dependent events and independent events, because you need to know both of them. Okay, stuff you need to know beforehand. You need to know the difference between multiplying fractions and adding fractions. If you don't, you won't be able to do tree diagrams. Now, multiplying fractions, you just do numerator times your numerator and your denominator times your denominator. So a half times a half would be a quarter, because 1 times 1 is 1 and 2 times 2 is 4. Adding fractions, you keep your denominators the same, okay, and if they're not the same, we're going to have to make them equivalent fractions so they are the same, and then you add your numerators. So a half plus a half, my denominators are the same, so I just do 1 plus 1, which is 2, so my answer is 2 over 2, which counts down to 1. Now I advise you to copy these down because these are mistakes that can happen. And just to refresh yourself, there you go, you can go and work them out. Okay. The only thing I'm going to ask you is that if you're typing this into your calculator, okay, and it's not an example here, but you're going to do a mixed number, like 1.5, use a specific 1.5 button on your calculator. Don't press the back button because you're telling your calculator to do something else. Pause the video. Right, here's your answers. Take your work, please. Okay, dependent events. It's when your first event affects the outcome of the second event. These are either always cards out of a pack or taking something out of a box, like taking cubes out or taking beads out of a box. Okay, dependent events. So remember, what this means your first event is going to affect your second event. So Rebecca has 9 coloured beads in a bag. 4 of them are black, the rest are green. She removes a bead at random and does not replace it. She then chooses a second bead. So let's draw this chart diagram out and then see what happens. The first thing we need to focus on is a bit where she says does not. Okay, that may change the difference between whether it's a dependent event or an independent event. Now, apart from the fact it's clearly a dependent event because it says it there, the does not means that the second set of results can be different to the first set. Now, all your diagrams look like this essentially. They might have maybe an extra branch, and they might maybe have like a third choice. This is what all your tree diagrams look like. And let's dissect this a little bit. My first option, my 2 outcomes are either a black bead or a green bead. Okay. Now, after my second choice, it's still the same. It's still black, green, black, green. Okay. In these type of questions, my first choice and my second choice will be the same. That's not true for all tree diagrams, but it's true for this one. So let's do it. Right. So my first choice. Yeah. So this branch here represents a black one being chose. I have 4 blacks and there's a total of 9. So the chances of that being black is 4 out of 9. Conversely, if you think about the green, these must add up to 1, yeah, which in this case would be 9 out of 9, which means it's going to be 5 out of 9. Now, if we go up the branch, and let's say we've got a black one first, okay, what's the chance of getting black again? Okay, now because there was 4 and I've already taken 1 out, that means there's 3, and there was a total of 9, but again I've taken 1 out, so it's going to be out of 8, so it's going to be 3 out of 8. Now, if you want to think about the green one being taken instead of a black the second time, you could think of it as there's 5 left in there because I haven't touched any green ones. But there is 1 less black, so it must be out of 8 again. Or you can think of it 3 out of 8 plus something must be 8 out of 8, which then gives you 5 out of 8. Now, let's talk about the ones on the bottom. I'm going to change the colours for this. It's like if green is taken first. So it's sort of like if there was a different timeline type thing, and instead of black being taken, it's green being taken. So let's say green's been taken once, but black is taken second. I haven't touched the black ones in this situation, so I've still only got 4 black bleeds left. But there is going to be 1 less because there's 1 less green, so it's going to be out of 8, which is 4 out of 8. And for green to be taken the second time, I have taken 1 green out, so there was 5, and there's 1 taken out, which means it's 4, and it's going to be 4 out of 8. And again, these add up to equal to 1. Next line we always fill out, and a lot of people forget this, but it just makes that you're working out. We just list out all the actual outcomes. So my first one is just going to be black, 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 green, green, black, green, green. It's written as probability as black, black, but it's fine if you just put BB for black, black. Okay. And then we work out the actual probabilities. And to do this, you just times the fractions. So for black, black, I'll have to do 4/9 divided times by 3/8, which is 12 out of 72. Okay. I wouldn't simplify them just yet. Black, green would be 4/9 times 5/8. Next one is 5/9 times 4/8, which is 20 out of 72. Notice these are the same. They're the same in a lot of them. And the last one's going to be 5/9 times 4/8, yeah, which is 20 out of 72. Now, I'd always tell you to check by adding all of these together. Yeah, because these are all your possible outcomes, so they must equal to 1. And if you add them up, yeah, they equal to 72 out of 72. Okay, let's actually deal with the questions. Calculated probability, Rebecca chooses 2 green beads. So green, it has to be the bottom one, which is 20 out of 72. And the second one is a black one, followed by a green one. Okay, which again is 20 out of 72. Okay, same one again. Here's another question. I'm not going to talk through as thoroughly as I did the last one. So Lucy has a box of 30, 18 are milk, and the rest are dark. Yeah, she takes one at random from the box, and then chooses a second. Draw a tree diagram. Calculate probability as 2 milk chocolates, and a dark one followed by a milk one. Give you a bit of time to work out. Okay, so my outcomes are milk and dark. So it's going to be milk dark again. And there's 18 out of 30. So that means that one's going to be 12 out of 30. Milk the second time is going to be 1 less than the 18 out of 30, which is 7 out of 29. Dark, I wrote it still 12, so it's going to be 12 out of 29. If you look at the dark one, I haven't touched any of the milk, so it's got to be 18, but it's 29, so it's 1 less. And dark is obviously 1 less, meaning 11 out of 29. And if you check, certain ones should up to 1. So these actually add up to 1, which they do, and these add up to 1, which they do, and they add up to 1, which they do. Work out the actual outcomes, which is going to be milk, dark, milk, dark. And to work out the probabilities, we multiply. So 18 out of 30 times 7 out of 29. Then 18 out of 30 times 12 out of 29. And 12 out of 30 times 18 out of 29. Oh, look, it's the same. And then 11 out of 30 and 11 out of 29. 2 milk chocolates is your top one, which is circled in red. 306 out of 870. And a dark chocolate followed by milk chocolate, which is a dark milk, which is 216 over 870. Now, I'd never really cancel these down unless the question asks for it. And these normally come up in the calculator paper, so I just type in the calculator. A couple ones I just want to point out. If the question says at least 1 milk, okay, at least 1 milk would be this one, added to the next one, and added to the third. Okay, and you've got 2 options. You can either add all 3 of these up, yeah, or I could take 132 away from 870. Because if I do the opposite, which is no milks, yeah, and take that away from 1, I'm going to get the same of at least 1 milk. Okay, here's some questions. Done. Right, pause the video. Here's your answers. Okay, second one, independent events. Now, these might seem a bit silly, and they can be thought of easier, but I always teach them second because I personally think they can be quite confusing and quite repetitive. Okay, probability it will rain on Monday is 0.2. Probability it will rain on Tuesday is 0.3. Right, now the probability it will rain on Monday will not affect the outcome whether it rains on Tuesday or not. I know you could argue that there's no relying condition that do both, yeah, but in this situation they will not affect. And for this, these are not dependent events; these are now independent events. And we still draw tree diagrams, we've just got to think about them slightly differently. Okay? Now, it depends how you want to do this, but I'd make Monday as in your first branch. Yeah? And there's 2 outcomes it rains, yeah, which we know is going to be 0.2. Now, logically, the other one's going to be it doesn't rain. Okay? Now, because they have to add up to 1, it's got to be 0.8. Because 0.2 plus 0.8 is 1. Okay? Right, now my second branch is going to be Tuesday. Okay, and the same 2 outcomes happen. Now these may not be the same 2 outcomes, but as a rule they are. Yeah, so rains, doesn't rain. Now we know 0.3, so by the same logic, we know if it doesn't rain, it's going to be 0.7. Okay, my bottom branch is exactly the same. And the important thing is, because whether it rains on Tuesday is not affected about how it rains on Mondays, your second ones will be identical. And this is true for every single independent event. Okay. List out your outcomes of rains, not rains, not rains, rains, not. Yeah, you might want to use different notation, but that's what I did. And the same as before, we just multiply. So for rains, I'll have to do 0.2 times 0.3. Okay, and use your calculator because people do tend to miss up a little bit here. Yeah, people will think it's 0.5, but it's not. It's 0.06. Okay, and then we do 0.2 times 0.7. Okay, which is 0.14. 0.8 times 0.3, which is 0.24, and 7.8 is 0.56. Okay, and double check as well, because obviously your last one, if I add them all up, this must equal to 1. Okay? And if you notice, none of these are the same, okay, which is slightly different to the dependent events that we just did. Okay, Let's try and do a different one. Okay, right. Now, if I have 5 red balls in a bag and 5 green balls, I take one out, replace it, and then take out another ball, draw a tree diagram to represent each outcome. Now, I replace this, and because I replace this, whatever happens in the first instance is not going to affect what happens in the second instance. Okay. Right. If you know what you're doing, draw your tree diagram now. If you don't, I'll talk you through it. It'll be a bit quicker. Same as before, my 2 outcomes are going to be red, green. And on my second choice, my same outcomes are going to be red, green, red, green, red, green. But just again, the second outcome is not affected by the outcome of the first. So my actual probabilities actually stay the same for each one. It's going to be 5-10 for my first green. It's going to be 5-10 for my second green as well. Now, the reason why people get confused with this is that every possibility is the same. Okay, you are literally just writing the same things over and over again, and people might feel that's a little bit pointless. Yeah, but it's perfectly fine. And of course, you've got 25 out of 100 because chances of one thing happening is the same, so everything else is the same. Okay, and probably easy to simplify at the end. Okay, now I would not simplify at the start here. Yeah, because if you chose this as a half, and let's say this wasn't an independent event, it was dependent, and you -1, then there you'd get 0 out of 1, which doesn't make sense. So simplify them at the end. Okay, last one to do. Peter and Becky run a race and play a tennis match, so they're two totally different. The probabilities of Peter wins a race is 0.4 and that Becky wins tennis is 0.7. And go put it out. Pause the video if you need to. Right, so for Becky to win the race, yes, either Peter or Becky, there's no other option, so you can do 1 minus 0.7. Chances are, same for the tennis, is that it's got to do 0.3 and 0.7 and 0.1. Work out your probabilities, check to make sure they're equal to 1, which they do. Okay. Oh, my 2 answers, sorry. The question says the probability Peter wins both events, which is the top one, 0.12. That Becky loses a race but wins a tennis. So loses a race, which is going to be Peter to win, but wins a tennis, which is that one there, yeah, which is 0.2. Cool. Here's a few more questions. I made them big so you can see them, but there's one extra one, and fourth one if you need them harder. Here's your answers. There we go. Hope you enjoyed that lesson.